So I had a really good question last night, and on my text, and I had it even better. Maybe 2 nights ago, whatever. I had an even better analogy. I was really proud of it. And the question was, it wasn't really a full understanding of why the frequency would stay the same, but the wavelength would lengthen in a faster medium. So we know that the speed of sound isn't truly stuck to that one speed, 1.54 millimeters per microsecond. It does actually travel faster in some materials and slower in other materials. And when it does that, the frequency stays the same. I know I've gone over this before, but I have to think about this when I'm saying it. So the frequency stays the same, but the wavelength changes. And so I thought about it, and I said, it's actually just like a basketball player. Basketball player is walking down the court, dribbling the ball. And as he's walking down the court here, let's say the ball hits the floor 2 feet apart. So basically that's a wavelength. That ball is acting like a wave because it's moving forward, because the guy's moving forward, he's dribbling, and it's going up and down, up and down. And if we could trace it out. So that's a wavelength of the ball at that point. Now let's say he continues, he's very steady. Let's do is 1 hertz. He bounces that ball up and down once every second. But then, let's see, how do I do this? Oh, there we are. But then he continues to bounce the ball at the same rate, but he's moving faster. So it's kind of like sound going from one medium to the next. Oh, okay, so still walking. Now, looks like I need to back up a little bit so we see more. Oh, looks like my ball went right into some other notes. Well, that's okay. We don't need all of this anyway. So now we go from still 1 hertz. The dribble rate is still once per second, but the athlete, the basketball player, is now traveling faster. Now let's say it's, 6 foot. So his wavelength is increased, but the frequency has stayed the same. And of course, the opposite's true. If you went from running back down to walking, maybe to a slow shuffle, then that wavelength becomes even shorter and shorter while maintaining the same frequency. All right, I think I need to get rid of that last ball since it's going to be in my way later on. So I thought I'd just share that. Now I have to get a basketball for the room. Not that I could even dribble. Basketball is one thing I never played. Okay. All right, so some questions from that. Number 150 in the back of the book. Trying to keep this, trying to time this so we get through all of these. I understand, I hear that COVID has, for those of you who are going to take the test soon, it's been delayed. Well,
all except mine. Mine is still a go for tomorrow.
Oh, all right. Well, let's hurry up. You can contact me for any last minute questions, but at this point it's hard, but we'll see. All right. So, what determines spatial pulse length? And let's see, I put a little hint with an arrow. What determines spatial pulse length? Well, this is one thing, right? And then the other thing is how long that pulse is. If that's one pulse, no. How long the pulse is determines how long. No, that's not what I meant. What I meant to say is how many cycles are in that pulse. So 1, 2, we'll call it 3. So cycles, oftentimes that's n times lambda. What's the actual question though? Both A and B. In diagnostic imaging, what determines the spatial pulse length? The ultrasound system. And there I go. Answering the question that actually, well, I did give it an answer. I just didn't look at what my answers were. The ultrasound system and the medium through which the pulse travels. Okay, so same difference. Same difference because the frequency is determined by the ultrasound system. This frequency and the number of cycles in a pulse are determined by the ultrasound system. And although wavelength and frequency are different, they are related. So, and then wavelength is determined more by the medium. So the number of cycles is determined, remember, here's my little transducer. And then behind that transducer is that backing material. That backing material is designed to make this ring as few times as possible. So instead of going, I don't know how well you could hear that. Instead of having a nicer ring like that, it's more just a real short click. So anyways, system and medium. Yeah, I kind of answered that wrong, but I wasn't wrong, but I answered it wrong, if that makes any sense. All right, 151. Which of the following best describes the spatial pulse length? Frequency multiplied by wavelength, PRF multiplied by wavelength, wavelength multiplied the number of cycles in the pulse, or duty factor multiplied by wavelength. So they wrote it the other way around, but basically letter C, wavelength multiplied by n number of cycles in a pulse. That's your spatial pulse length. That's the one that's right here. Let's see. Wavelength, and then 1, 2, 3. That's all the information you need for your spatial pulse length. 153, I skipped 152 apparently. Using a specific transducer, what happens to the spatial pulse length as the sonographer increases to the maximum imaging depth? What happens to spatial pulse length? So I just wrote down spatial pulse length, delta depth, changing depth. What happens to this guy when we change the depth? Absolutely nothing. Let us see again, right? Nothing changes. Spatial pulse length is the spatial pulse length. That does not change. Axial resolution is axial resolution. Axial resolution is equal to 1/2 the spatial pulse length. But axial resolution does not change no matter what your depth is. Your lateral resolution changes, your slice thickness changes somewhat, but lateral resolution definitely changes. Axial resolution does not change because your spatial pulse length does not change. This length, the time in between, that does change. So in 55, on what does the pulse repetition period depend? Now that's a tough question. Well, it's not a tough question, except once again, my initial, I wanted to say, it depends on depth. Spatial pulse repetition depends on the depth. When we go deeper versus shallower, that period is all of this, the resting and the active state, or the listening and the pulsing state is one pulse repetition period, and that changes with depth. So that was my first reaction to this question. But when we look at the answers, it's the source, the medium. Is this a source or medium? It's the medium. I mean, it's the source. It is the source. In other words, the machine is deciding what the pulse repetition frequency is, which of course decides what the pulse repetition period is. Do I go into this now? Yeah, I'll just remind you now. I can't remember if we're going to go over a question or not, but let's remind us. Let's think about this again. If I'm going deep into the body, we need more time, right? We need time for all of those echoes to come back. The deeper you go, the more time you need. So this would be an example, let's say, of deep, and this is unrealistic. You know, of course, if this were built to scale, there'd be a mile difference between these two pulses, but obviously we can't do that. So if that is deep, and then we go shallow, we need less time. And this time, of course, is that time, that listening time. But if we're going shallow, we don't need all that listening time. So now we have much shorter listening times because we don't need it. Those echoes they've all come back. Why wait? Let's see, what do I have? 155, 156. A sonographer adjusts the maximum imaging depth to an ultrasound system. Which of the following also changes? Okay. Now this one you just got to pay attention to because it's very easy to just pick one and not the other. We just talked about this, of course. The pulse repetition period. Your book, your images from your book usually depict that from here to here. When I draw it, I prefer from here to here. It does not matter as long as you're including one listening, whoops. As long as you're including one listening period and one pulse. So it really doesn't matter how we do this, whether it's from there to there or there to there, it's the same difference. But I just can't stand drawing it that way because my sound always travels this way. And the definition is from the beginning of one pulse to the beginning of the next pulse is the entire pulse repetition period. I don't know, maybe I should start drawing it the way the authors do it. That way I won't confuse you guys. But anyways, a sonographer adjusts the maximum imaging depth. Pulse repetition period is changed. And if you're going to change the pulse repetition period, you're going to change the pulse repetition frequency. That's just the way it is. They are reciprocals. Frequency goes up, period goes down equally, and vice versa. Okay, looks like I jumped all the way to, yeah, I jumped to 159. So we have some information here. 2 ultrasound systems, one producing sound with 3 megahertz, the other producing sound at 6 megahertz, and both of them are imaging to a depth of 8 centimeters. So 159. The period of the 3 megahertz sound is greater than the period of the 6 megahertz sound. Okay, math is probably the easiest way to do that one. But if you don't want to do the math, and because the math confuses you or you're confused, just stop and say, okay, I'm going to draw a squiggly line and call it 3 megahertz. And then I'm going to draw another squiggly line and call it 6. But what is that? What is it going to look? Is it going to look the same? Of course not. It's twice the frequency, which means that in this distance, this is a distance scale now. I don't know if that's exactly right, but that's okay. Because all now we need to do is we're going to look at the period. Now what's the period of the 3 megahertz sound is greater than the period of the 6 megahertz sound. Like I said before, this is on a time scale of whatever. Well, yeah. This could be a 1 second. Well, no, it wouldn't be 1 second. It could be some amount of seconds. Doesn't matter. It's a time scale. Yeah, time scale, because with 3 megahertz, fewer cycles go by than with 6 megahertz in a certain amount of time. So anyways, I'm just talking in circles now. Let's just finish what we're saying here. The period yes, it's also wavelength, but in this case, we're talking about period or time is greater than here. So the answer is true. The other thing we could do is just simply look at this and say that, let's just write that again. The pulse repetition period is equal to 1 over pulse repetition free. Oh. My bad. I'm close. I'm very close, but I just used the wrong. It's the same equation, but I just used the wrong units. I'm sorry. In this case, we're not talking about pulses. We're just simply talking about the sound. This could be a pulse. It could be continuous wave. It doesn't actually give us that information. So my bad. Period. So close to that. Period is equal to 1 over frequency. I could use a P or a T here. All right, and so we know if the frequency goes up, the period goes down. If the frequency goes down, as in 3 megahertz, the period goes up. So remember, you don't have to throw numbers in there if you don't want to. Just use those arrows to remind yourself if the frequency, in a reciprocal like this, if the frequency goes down, the period is going to go up. Stop me if I confuse you, if I say something that you are not sure about, let me know. You could also text me. I've got remember to put the phone on silent this time, but it is facing me. So if you text me or chat with me, I should see it. Okay. 160, the wavelength of 3 megahertz ultrasound is greater than, well, okay. That also is true. Wavelength is greater. Same tissue, right? The reason I'm saying that, same tissue, you can't compare these if one's in liver and the other is in bone. Then you can't compare the wavelength at all. Why? Because right where we started with, this is basically tissue 1, tissue 2. The velocity has increased considerably. The frequency hasn't changed. The velocity changed. So just remember, that's a different scale. And if you're going to have a different scale in velocities, it means you're definitely not in the same tissue. Usually, outside of this situation, we're usually talking about the same tissue. And when you're talking about the same tissue, then you could directly compare these because they're traveling. Why? Because they are both traveling at the same speed. Change the speed and then everything else gets all a little confusing. All right. Let me tell you just one last thing. Most of your questions on the SPI are going to be like this, same tissue. So when you're talking about wavelength between 3 megahertz and 6 megahertz, this is what you're talking about. If you're talking about the period between them, this is what you're talking about. It's only when we're talking about different tissue velocities that wavelength changes independent of frequency. So most of your questions are going to revolve around this. Trying to balance teaching you something and not teaching you too much, and then you get on the SPI and you forget which one's which. So keep that in your head. All right, so 160 is true as well. 162, a pulse repetition frequency of the 6 megahertz transducer is greater than the pulse repetition of the 3 megahertz transducer. Pulse repetition frequency. So let's say this one's my 3. And then that one's my 6. Remember, your pulse repetition frequency does not equal frequency. In other words, the megahertz that you're working with does not affect how many pulses there are in a second, because they go the same speed. 3 megahertz and 6 megahertz are the same speed. It takes the same amount of time for their echoes to come back. And so the frequency and therefore the pulse repetition period, they're equal between the two, notwithstanding just the tiniest changes in spatial pulse length. But that's negligible. They don't even, it's not even worth talking about. So it's pulse repetition frequency has nothing to do with frequency. It has everything to do with depth and how long things come back. So that is false, right? I can't remember how it goes. False. All right. So let's see, 163 and 164 I kind of put together. Why did I do that? The maximum imaging depth during an exam is unchanged. Depth unchanged. A new transducer with a longer pulse duration is used. Look at the next 4 statements. So depth is unchanged. Transducer with a longer pulse duration. Yes, a longer pulse duration. 163, the pulse repetition period is increased. No. False, depth is unchanged. And depth is your pulse repetition frequency or pulse repetition period. Depth is unchanged, so that won't change. 164, the pulse repetition frequency is increased. Well, no, so that's why I put them together. They're the same question. Period is increased, frequency is increased, nothing is increased when it comes to pulse repetitions. 165, the duty factor is increased. duty factor. What is duty factor? What? So in the most general terms, it's the amount of time talking divided by the amount of time listening. Well, listening in, divided by the whole time, the whole period of time. So mathematically, pulse duration. Did we already talk about what pulse duration? I can't. All right. Pulse, what is pulse duration? Pulse duration is the number of cycles in a pulse. Of course, that's going to affect not only the length of the pulse, but also how long that pulse lasts. So the number of cycles. Since we're talking about duration, we're talking about time. So the time per cycle. So number of cycles times the time per cycle. Time per cycle. That I know we just did because I kind of screwed that up. Here we are. I'm going to put a small t down here. Okay, so period t. 1 over frequency. So if you don't have the period, but you have the number of cycles, but you have to find the pulse duration, don't panic. 1 over frequency is your period. So pulse duration. Let's just write that down. N times T. Number of cycles times the period of time for each cycle. And then the below divided by the whole thing, pulse repetition period. Times 100 is optional. You don't, sometimes you will have that and sometimes you will not. So you gotta be careful with that. So this is basically percentage, well, if it's times 100, it's percentage of time talking. In quotes, or pulse. Whoop. There we go, pulsing. Let's see. So what's the actual question? The duty factor is increased. What's going on? Depth, longer pulse duration. Yes. You don't have to do the math. Longer pulse. Longer pulse duration. Longer duty factor. The maximum pulse duration, by the way, is no longer a pulse, it's continuous wave. So then that would be 100% of the time talking. Say I jump to 167. What are the units of pulse repetition frequency? Frequency. What are the units of pulse repetition frequency? And of course, they're not giving you the correct units, are they? None of these are correct. One of them's potentially correct, but none of them are actually correct. Seconds, 1 over seconds, millimeters per microsecond, seconds to the -2 power. Okay. Time, simply put, time alone is not a frequency. If if I say, I don't know, I can't think right now, but time alone isn't a frequency. Millimeters per microsecond, that's a distance over time. That's not really, it's not really our frequency. And the last one, seconds to the -2, that's just part of a greater equation there. So 1 over a second, 1 divided by seconds. 1 time per, well, that's 1 hertz. So it's not realistic for a pulse repetition frequency. That's why I say none of them are true, but it's the only one that is actually a frequency. So 1 over second, that's 167. 1 over second, technically speaking, is 1 hertz. So that is a frequency. It's the only, sometimes you're not given the perfect answers, guys. You have to figure out what the best out of the mess is. Okay, I don't think I have too many more. In effect, when the numbers are really close like this, it usually means we're going to go through them fairly quickly. 168. Well, this one's easy, but you have to read it. The pulse repetition frequency of ultrasound produced by a transducer, typical of diagnostic imaging systems. So it's a little bit awkward. It's not so much awkward, it's just, it feels like it's asking more than it really is. The pulse repetition frequency of ultrasound produced by a transducer, typical of diagnostic imaging systems. And A, can be changed by the sonographer, depends on the medium. Well, we know it doesn't depend on the medium. So let's write pulse repetition frequency as, you know, I could really argue against that one too, but pulse repetition frequency is produced by the machine. Is unchanged as long as the same ultrasound system is used. No, we just got done talking about how depth will change the pulse repetition frequency, and D has nothing to do with clinical imaging. Well, I think it does. So A, can be changed by the sonographer. Yes, when we change our depth, we change our pulse repetition frequency. It's actually a really easy question for us. But I suspect, because when I read it, I had to read it twice. And I'm like, what the heck are they asking me? It's just kind of a little roundabout. But all they're asking, the pulse repetition frequency, blank, can be changed by a sonographer. Yes. So you could take the first 4 words of that sentence and forget the rest. 169, in diagnostic imaging, what establishes the pulse repetition frequency? It's just the machine establishes it. One could argue that if we were made of diamond, the pulse repetition frequency in use would be different. That would be a different medium, but since we're all made the same, it's always assumed the same velocity of sound, speed of sound, then it is simply the source of sound which creates the pulse repetition frequency. You change the depth, but still the source is what's doing it. 170, when a sonographer increases the maximum imaging depth during an exam, what happens to the PRF? So max depth, we need more time. If we need more time, I should have put. Okay. If we need more time, that means PRP has to go up. That's the same thing, period, time. which means if that goes up, this has to go down. So frequency has to, just mathematically there, we can see that frequency has to reduce. And just thinking about it, it's going to take more time. The deeper you go, the more time it takes for all those echoes to come back. That was 170. Yep. I jumped to 173. What is a typical value of the, there's a reason I chose this one. Typical value for the duty factor, also called duty cycle, of pulsed sound waves used in diagnostic imaging. Okay. First, let's look at units. Duty factor. What units does duty factor have? No units. It could be given in two ways, as a percentage, which really isn't a unit, or it could just be given as simply a decimal number. Yeah, but no units. So A and B, we can drop immediately. And we look at C and D. I had like, I don't know. I wouldn't have, out of a bag of numbers, I wouldn't have chosen 0.001. That seems even too small, but definitely not 0.05. If the answer, if you said 0.75, that's basically your duty factor without a percentage. Both of the last answers are non-percentage. So they, like I said before, this part is optional. You don't have to do the times 100. That's why you have to be careful. And if you don't do times 100, then you have a decimal number to deal with. And so we have two decimal numbers given, 0.05 and 0.001. Well, if we did multiply by 100, the duty factor in this case for letter D would be 70, I'm sorry, letter C would be, I'm sorry, itchy, 75% of the time. That means talking 75% of the time. That's more than me. That probably isn't more than me. But that's an impossibility. You can't, remember, we're listening 99% of the time, 99.8% of the time. And basically, this is times 100. This is still like 0.1% or 0.01. 0.01%. Yeah, that's really small, but possible. It's possible. So D is correct, right? Please tell me it's D. Yes, D. So even if you don't know your numbers, you should know that this is way too high. And I think I ended it on, yeah, I skipped to 179 and that was that. Why? What do I want to look at this one for? While using the same ultrasound machine and transducer, which is more information than you need, which of the following can a sonographer alter? More than one may be correct. Okay. I remember why I wanted to include this one. Sometimes you could turn the question, as long as you remember you're doing it, turn the question backwards. Which of the following can you not alter? Can't, remember, we can't change frequency. Same transducer, same machine. I know, yes, we can technically, but according to Element, we can't change the frequency. So remember that. Pulse duration. Pulse duration is decided right there in the transducer. That backing material keeps that transducer element from ringing. That's what causes the 179, the pulse duration. So we could look at it that way. We turn it around and then say, well, then look, A, B, and D must be things that we can alter. Pulse repetition period, pulse repetition frequency, or A and B are basically the two sides of the same coin. Yes, by changing our depth. And scared me, D. Duty cycle. Duty cycle. Well, the duty factor. Duty factor. We just said that we could change our pulse repetition period. If we could change our pulse repetition period, then we could change our duty factor. Any questions on that stuff? Going too fast, too slow? I can't hear you guys, right? Can I hear you guys?
You're going
I don't
Okay.
think most of us have had coffee yet.
Okay. I know. See, that's why I don't go through too many of these. This can get pretty boring, and this would be teaching over the internet is hard enough. Reviewing is even harder because on a review, it really should be getting constant feedback, but I don't know. I'm still not very good at this distance learning stuff. Okay, guys, let's get our cell phones ready. Get on to we're going to get on to, what are we going to get on to? Kahoot. 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 Teach. Review chapter 8. So not a particularly long Kahoot today. Classic. Each one of you will be on your own. One, 3, 2, 3, 5, 4, 7. Sorry. Just hit the wrong button. Let's do some disco. All right, let's get started. Mostly chapter 8, maybe all chapter 8. I can't remember. Let's give this a try. Once again, most of your true false are going to be short. So I think one of them I left at 20 seconds. Most of them are 10 seconds. So you got to read quick. And the others were multiple choice are typically longer. So. Example of transducer. Best answer.
I already messed up.
I wasn't sure how to ask this question. Wasn't sure how to, I was just getting tired. I couldn't think of how to ask this question and make sure that you guys understood. But yeah, a PZT, piezoelectric, lead zirconate titanate crystal is what we use for transducers. But everything on this is actually technically a transducer. Anything that changes energy from one form to another is a transducer. Your ears, the mechanism of your ear, your eyes, muscle, light bulbs, all of them are transducers. Kind of a sneaky is. Now, is that a pronounced H or is that a silent H? Are you the artist formerly known as Heather, or?
Formerly known.
When 13 microseconds are put into the range equation, the product is 10 millimeters or 1 centimeter.
Shit.
Yes, it is actually true. That's why the 13 microsecond rule exists, because that just happens to be the number. When we put it into the equation, it gives you 1 centimeter of back and forth travel. Oh, I thought there was a bird outside. It was just a fly around my head. All right. Piezoelectric materials. Actually, I meant to give you guys more time to read all those. That was my bad. Yes, piezoelectric materials produce a voltage when deformed, and that's when the echo comes back. It slightly deforms, in other words, rings it and then produces. They are dampened for imaging. That's our damping layer. Will produce voltage when exposed to light. I'm sure there are some, but that's not where I was going. Okay. Emily's on fire. The matching layer is good. Most of you have an intermediate impedance between the element and skin. Definitely not made of stiff material. It's actually made of a rubbery material. Once again, halfway between skin and the element itself. Still in the lead. The backing material is responsible for okay. Yes, I'm sorry, I got a little distracted there. Backing material is responsible for a short spatial pulse length. That's why we do that. Increased sensitivity? No, it decreases our sensitivity. So the backing material is really, it has a lot of bad features, but that one feature of a short SPL is so important that they do it anyways. Emily is taking lead. The useful happy accident of backing material. Oh.
It's not giving me like my options. It's still keeping me on the other screen.
Oh, no. All right.
You gotta refresh it.
Oh, thanks, June.
Yes. Plurality of you chose wide bandwidth. That's a happy accident. And of course, what do we do with that bandwidth? Multi-frequency transducers, and being able to listen to multiple frequencies too. So that's really nice. It actually produces low quality sound, so low Q, decreased sensitivity, and well, the opposite of narrow bandwidth, of course. All right, Emily stays in the lead. The broad bandwidth transducer can, oh, I just answered this.
Can we go back? I clicked the wrong one. Plurality again shows multiple frequencies. So yeah, I just said that, guys. That broad bandwidth allows us to use those frequencies off to the side if we choose to. Can't do that with a narrow bandwidth because there is only one frequency. Broad bandwidth transducers can't image deeper. They don't produce better Doppler. In fact, you could say that a narrow bandwidth probably, I'm getting into other concepts. And no, continuous wave transducers are actually not broad bandwidth at all. They are narrow bandwidth. All right, true or false, low quality may not be sensitive, but is necessary result of achieving a small. Yep. Losing that quality, losing that sensitivity is worth it because that small spatial pulse length. All right, Chelsea's on fire. True or false? Piezoelectric materials are created at the Curie temperature. You better get this. I messed up again.
John. Piezoelectric materials are created at the Curie temperature. That is true. It's like over 1,000 degrees is where the material becomes plastic enough where then you put it through the high electromagnetic field that aligns the atoms and forms a certain type of crystal. We didn't really go over that. It's because you don't need to know that, but it's just it's a diamond-shaped crystal like this, and when you push on it, it forces electrons out, creates a voltage, and then when the voltage is forced in, it widens this direction, so creates a sound wave. It's kind of really cool.
Major difference between pulsed and continuous transducers. Good. Continuous wave transducers have no backing. They have no axial resolution, and pulse transducers do alias, and pulse transducers are less sensitive. All right. Two elements, six meter. I wish I could pause. You guys have to read it yourself. Oh, shoot. Wait, what? Oh, element B is 2 millimeters thick. Oh, I read my own question wrong. and I made this up this morning. Element A is 4 millimeters thick. Element B is 2 millimeters thick. So the width of the element has nothing to do with frequency. So can't be B. Well, it's not going to be B. Let's go to element A produces a higher frequency. Element A is thicker than element B. The thicker it is, the lower the frequency. So no. Element B produces a higher frequency. Yes, element B is thinner in thickness, thinner thickness. So it will produce a higher frequency, and then B. Just a little, obviously you guys are a little bit rushed right now, but if you ever do see a question like this and you have more time to look at it, the blue and the green cannot both be correct, right? They cannot both be correct. Therefore, it's got to be one of those. So the other two you could ignore at that point. Wait, did I just hit a? True or false? The speed of sound and PZT affects its frequency. Oh, this is a tough one. It's true, but this was a really tough one. In fact, you guys are seeing this, right? Yeah.
Yes.
Right after writing that, I pulled up my, let's get rid of my last, I can't get rid of my last basketball. There we go. Okay. Frequency, wavelength, speed of sound. We know from the beginning of the book of this relationship here in the middle. Frequency. Okay, it's weird. Frequency is equal to speed of sound divided by wavelength. When it comes to transducers, it's the same thing. Oh, I wrote the bottom row backwards, but it's the same difference. Frequency is equal to the speed of sound divided by wavelength, except wavelength is affected primarily by or entirely by the thickness of the element. Wavelength is 1/2 times the thickness. And if we draw the sound wave coming out of it, we kind of see why. This is 1/2 a cycle. There's the other half of that same cycle. So this whole from here to here is one cycle, but half of it at any one time is produced inside the element. And the same thing over here. There's half a cycle. There's more or less there's a full cycle. And so visually you could see why a thinner transducer will create a higher frequency. I'm sorry, higher wavelength or smaller wavelength, smaller wavelength. But if we look at the math here, so 1/2 thickness, I'm just going to put, that is the wavelength. So these are equivalent. These are really the same exact equation. But the speed of sound is something we normally take for granted. We normally just say, well, it's the same. It's always the same. It doesn't change. And so we're just going to use it. There's a number and we're going to ignore it. But it does affect, I mean, it is in the equation. It does affect things. Mathematically, putting an arrow here and an arrow there is correct. It's just realistically, we don't do that because the speed of sound is determined by the medium. Well, the speed of sound here is determined by the medium, the PZT, but it is in the equation. It does affect frequency. So that was a hard, that's, I don't know. Put it this way, I got it wrong. When I was just going through it, I'm like, yeah, no, it doesn't. I'm like, and then I saw the answer. I was like, I had to think about it, like, oh, of course, right. You got to go back to the equation and really think about it that way. So when you do take the exam, by the way, you can't bring anything in except your brain. If the triangle helps you, draw the triangle. If you're asked about questions specifically about the speed of sound in the element or element wavelength or anything, draw the triangle again with speed of sound, frequency, and wavelength, but rather than wavelength, it's just 1/2 a thickness actually is the wavelength. So if these triangles help you, remember them, go in there, they'll give you a blank piece of paper or maybe a small little whiteboard and write that down immediately. And not to mention some other equations too. Okay, let's see, I want to go back to Kahoot. I think we're maybe one more. Yes, one last one. Oh, come on. All right. Didn't realize I was giving you the answer, but that's okay. All right, good. 11:15. That's not bad. Not a bad use of our time. Like I said, guys, I'm gonna have to work out a schedule for the next couple of weeks. I mean, I'll be here until the 20th, but really try to get ahead of some of. I'll just produce some of these you can do on your own for asynchronous assignments, and then I'll try to produce some lectures, which are really more review. So, and hopefully it'll be bearable to listen to. So. All right. Any questions? We all good?
I think so.
Nothing.
All right. What did I do here? Oh yeah. You guys, more than a couple of you had troubles. That's all right. As long as you're paying attention to the game. All right, guys. We'll see you. Have a great weekend. It is Friday, right?